Hi everyone, my name is Cheikh Mbake. I'm a water treatment engineer, and today I will be presenting you this webinar that talks about sludge management and biomass inside of the System O. Through this webinar, I will start by telling you about what's the System O for those that may not know what it is or how we came up with this technology. After that, we will talk about the biological mechanism pertinent to the System O technology, where I will get into the details about aerobic and anaerobic alternation, intermittent feeding, predation, elimination of the mineralized byproducts, and from there we will go through the natural management of sludge inside and outside of the pipes based on the previous mechanism. And we will finish with the controlled proliferation of the biomass that prevent your system from clogging due to an excess of biomass. At the end, there will be a period of questions where you can feel free to ask questions about the presentation or any other question related to the System O or the project you are actually working on. At DPO International, we strive to be a reference in the field of wastewater treatment in order to improve the quality of life for all by following natural and ecological principles for the respect and the well-being of the planet. Our mission is to create and implement innovative technologies, environmental friendly wastewater treatment and reuse solution for any situation anywhere in the world. Some of you may be familiar with these conventional leaching fields that were and still are very popular in many areas. These systems have many weaknesses. The most important of them are presented here. At first, we had the water distribution problem. It was very difficult to ensure an even distribution of the wastewater by just using a classic PVC tee. The influent always tends to go to one way more than the other. The second main problem was the fact that the water would flow directly through the first perforation of the perforated pipes and then get into the natural soil with its pollutants. It was leading to a progressive clogging of the natural soil until the entire installation is clogged. Another weakness was the fact that there were no treatment inside of these systems due to a low dissolved oxygen concentration inside of the pipes. There were no proper ventilation and no bacterial support. So, trying to solve these problems, we came up with the advanced unbioseptic pipe. Each component has its role in order to have a better and long-lasting wastewater treatment system. In here, you can see the large diameter perforated pipe that increases the airflow inside of the system. Here, you can see the bioaccelerator that distributes the water lengthwise using the capillarity principle. All around the pipe, you can see here, it's in green, the synthetical bacterial support that assists the bacterial growth. And all around the pipe, here, you can see the geotextile membrane. It allows the water and air to flow to the sand and then, at the same time, prevents the sand from entering inside of the pipe. That's how we went from the conventional leaching field that was made using a perforated 4-inch pipe to the System O, by solving the main problems that we used to have with these conventional systems. This is what a System O looks like. Once the water leaves the buildings or the houses, it gets into a septic tank. From that septic tank, the water is going to flow through a distribution box that is going to evenly distribute the water between the different rows of System O. Inside of the pipes, the water is going to be treated, and after that, the water will go through the pipe, through the system sand, and then get collected and is available for reuse. The System O is a 100% biological and autonomous system with no electricity, no moving part, no ongoing maintenance, no odor, no noise, no chemical additives, no waste discharge, and no filter media replacement. This video will give you a better idea of how it works. Now, let's talk about the biological mechanism. The alternation between aerobic and anaerobic condition as a part of wastewater treatment systems is a mechanism commonly used as a procedure to reduce the production of septic sludge. These conditions upsets the metabolism of bacteria by changing the mechanism of glycolysis between the cellular respiration and fermentation. A disruption such as this forces the bacteria to prioritize catabolic pathways, breaking down molecules to ensure the supply of energy needed for survival, as opposed to anabolic pathways associated with biosynthesis, which are responsible for the production of sludge. This phenomenon is known as respiration uncoupling and is one of the main mechanisms involved in the minimal production of sludge in the famous oxyacetylene anaerobic process. The alternation between an aerobic and anaerobic environment occurs multiple times each day, resulting in a repetitive respiration uncoupling. Each time water is used in the house, water leaving the anaerobic septic tank spills into the advanced and bioseptic pipes. Depending on the type of supply, the water is agitated, allowing a partial aeration. Part of the water becomes an aerobic environment, where the first respiration uncoupling occurs. As the oxygen is consumed by the microorganism, the water becomes progressively anaerobic. It's not until the moment when the water infiltrates completely into the sand that the advanced and bioseptic pipe becomes a mainly aerobic environment, causing once again a respiration uncoupling among the microorganisms present inside and around the pipes. The pollutants are then broken down with the help of the aerobic pathways. Due to this change in their environment, the microorganisms need to once again change their glycolysis pathways. This phenomenon occurs each time there is a significant amount of water entering the system. Now let's take a look on the intermittent feeding. The frequency of the supply of nutrients is equally recognized as an important factor in reducing the production of sludge. In fact, a method that encourages intermittent fasting, continuously pushing the microorganism to store energy in form of ATM rather than expanding excess of energy for reproduction, is optimal, according to the respiration uncoupling principle. Being limited to substrates that have already been assimilated due to the absence of external nutrients during the fasting period, the microorganisms concentrate on catabolic pathways to sustain their survival process. The System O equally applies this principle, particularly during the night where the microorganisms undergo a long period of fasting. Not only does this fasting period lower the reproduction in microorganisms, but the next waves of nutrients are also mostly used to rebuild the reserve of energy, once again reducing the production of biomass. The periods of fasting encourages the long-term predominance of slow-growing microorganisms that are better adapted to this type of feeding and environment. Another biological mechanism is the predation, which is a principle that is more and more implemented as a way of reducing the sludge production in wastewater treatment plants. Although bacteria are by far the most numerous organisms present in domestic wastewater, the presence of other microorganisms isn't negligible. In fact, protozoa, rotifers, and nematodes are also found in a large number, playing a significant role in wastewater treatment systems. These microorganisms are found higher in the food web than bacteria, consuming both live and dead bacteria. They also integrate minerals excreted by bacteria into their metabolism. While there is an energy transfer from one trophic level to another, a reduction of living biomass is observed, knowing that the microorganism reproduces proportionally to the amount of nutrients. A certain equilibrium establishes itself inside of the system, allowing the biomass to remain relatively stable. An advantage of the advanced and bioseptic technology is that it acts completely as an ecosystem. Now we are going to talk about the mineralization. The mineralization is a term used to describe the degradation of organic materials, leaving byproducts called minerals. For sure, an accumulation of these byproducts could be observed over the years under some conditions. However, this is the case for a system that is open to the environment like this one. In fact, these byproducts in the forms of minerals are excreted during the biodegradation of organic materials. We are most notably talking about CO2, nitrogen compounds, potassium, phosphorus, and different metals. Although these are not all necessarily assimilated during the first mineralization, these compounds are always accessible and very useful for different organisms in the ecosystem in which the system or pipes are installed, as discussed in the previous slides. Essentially, these minerals are redistributed throughout various metabolic cycles in the organism. For example, the nitrogen and the denitrification process allows compounds to be easily assimilated by microorganisms and by many roots that access the interior of the advanced septic pipes. The diagram below explains the process of mineralization and the assimilation of organic and inorganic materials that occurs naturally in the soil and is exactly what occurs inside of the system or technology. Now we're going to talk about what's going on inside and around the pipe. The microorganisms inside and around the system or pipes are the first to treat the effluent leaving the septic tank because that's where it all starts. In the vast majority of time, the biomass is mainly composed of aerobic and facultative bacteria, as the ventilation system provides a well-aerated environment inside of the pipes. The water coming from the septic tank is treated by this biomass first. The importance of the treatment depends on the water's retention time, which in turn depends on the sieve analysis of the system sand and the permeability of the biomass. But the bacteria are not the only ones who treats the water. The system sand under the system or pipes also contribute to the treatment. It actually serves as a filter by catching insoluble pollutants and increasing the water's retention time. This is why having an approved sieve analysis for the system sand is important. System sand limits the flow of water to allow the biomass enough time inside the pipes to properly digest the pollutants. Moreover, system sand is ideal for microorganisms as it provides a very large contact area and it helps the bacteria to hang on. Since we are now deep under the ground, the oxygen is generally less so that we are mainly in an anaerobic environment. Anaerobic bacteria can develop and thrive, allowing for a second type of treatment. This mass of anaerobic bacteria in the sand is known as biomass. The biomass is mainly composed of anaerobic bacteria as well as their extracellular matrix. As it digests pollutants in anaerobic mode, this layer grows more and more at the beginning as the biomass in these pipes is still small. The more it develops, the more the sand's porosity goes down, increasing the water's retention time inside of the pipes, which improves the first aerobic treatment and the filtration of pollutants. This improvement of treatment in the pipes by increased retention time is important as it reduces the quantity of pollutant that reach the biomass. This is an extremely important phenomenon in the context since, although it is essential to the treatment, the growth of the biomass must absolutely be controlled. For most conventional systems, it is this uncontrolled growth of biomass that clogs the native soil, caused by the absence of treatment before the wastewater infiltrates into the soil, as well as the absence of aerobic conditions. The system of solutions have many characteristics that help them avoid excessive sludge accumulation and clogging by uncontrolled growth of the biomass. First, as discussed in the previous slides, we have the alternating between aerobic and anaerobic conditions, prioritizing catabolic pathways and breaking down molecules as opposed to growing the biomass. In addition, passive ventilation of the system is key in contrast to the majority of conventional systems. The vents allow for constant aeration in the pipes, which reduce the growth of anaerobic bacteria, controlling the thickness of the biomass. Finally, it must be noted that the system is often at rest. When there is no wastewater making its way to the pipes, it could be at night or during prolonged absences, the system O doesn't receive no organic load. This means that the bacteria fast for periods of time, which limits the growth of the biomass and enables the aerobic bacteria to regulate it. During this time, due to the favorable conditions and the reduced availability of nutrients, the aerobic bacteria rely on the biomass, reducing its thickness and controlling its growth. With all these processes, the size of the biomass becomes balanced under the advanced and bioseptic pipes. This allows for optimal treatment without degradation over the time. Here, we will show you an example of an inspection of a 15-year-old system. Back then, they were not installed with a bioaccelerator.